For decades, computing power was defined by geometry. If an organization needed to process more data, they had to physically find room for the hardware. In the 1950s and 60s, this meant buying a mainframe. These machines cost millions of dollars and required entire rooms dedicated to their operation. The sheer upfront capital expenditure meant only giant corporations or governments could afford high-level computation. By the 1980s and 90s, the client-server model shrank these machines down so every employee could have a PC on their desk. But the core problem persisted. Processing power remained inextricably linked to physical, localized machines. Under this on-premises model, scaling a company's infrastructure was an operational nightmare. Anticipating a traffic surge meant ordering new physical components, waiting weeks for shipping, and manually installing server racks. Furthermore, a local server possesses a strict finite amount of CPU, RAM, and disk space. Once an application hits the limit of those specific components, performance degrades rapidly, creating a hard ceiling on processing capability. Traditional on-premises architecture forces a rigid dependency between digital processing capability and physical real estate. To bypass this physical bottleneck, engineers had to solve a difficult conceptual problem. They needed to decouple the software from the physical machine it ran on. Two technological prerequisites made this possible. Early internet connections were too slow to stream computing power. The eventual deployment of fiber optics eliminated data latency, making remote processing feel as fast as a local hard drive. The second prerequisite was grid computing, the networking of millions of servers across different geographic locations so they could be treated as a single, massive pool of processing power. But the critical mechanism that actually severed the tie between hardware and software is a technology called virtualization. Without virtualization, a physical piece of hardware is typically dedicated to running one operating system. Virtualization introduces a software layer that abstracts the physical hardware. This allows one solid server to act as 50 independent virtual machines, each running its own operating system simultaneously. By partitioning massive data centers into these virtual instances, providers like Amazon Web Services began renting out exact increments of processing power. Organizations stopped paying huge capital expenditures for physical hardware and began paying for computing as an operating expense, exactly like an electricity bill. Virtualization shattered the geometric constraints of the server room. It transformed computing from a static physical object into an elastic shared utility. Operating this shared utility requires a highly specialized architecture to manage how millions of users interact with the remote hardware. This block diagram illustrates an architecture divided into two distinct environments connected by a network, usually the internet. The front end consists of the client-side infrastructure. This is the web browser or application interface where the user inputs their requests. The back end is the cloud itself. Controlled entirely by the provider, it houses the massive data storage, virtual machines, cloud runtime environments, and security mechanisms required to process those client requests. To function correctly, this backend must adhere to strict engineering characteristics. First, it requires on-demand self-service, meaning users can provision resources automatically without human interaction, and broad network access, ensuring availability from any device. Next is resource pooling, or multi-tenancy. Multiple distinct organizations share the exact same physical instances of hardware and databases, kept separate and secure by the virtualization layer. Finally, the system relies on rapid elasticity to automatically scale resources up or down based on current demand, combined with a measured service model that constantly monitors and optimizes usage to ensure accurate billing. The cloud is a highly automated, dynamically pooled environment governed by strict algorithmic resource allocation. Because different users require different levels of control over this massive back-end, the architecture is partitioned into standardized abstraction layers. This structure is perfectly mapped out in Sir Rajkumar Bhuia's Cloud Computing Reference Model. At the base of the model is the most fundamental layer, Infrastructure as a Service, or IaaS. Here, the vendor provides the raw computing resources. Users get direct access to virtualized server space, storage capacity, and networking bandwidth. IaaS is utilized by IT teams to completely replace their on-premises physical server rooms. It requires heavy technical expertise to manage, but it offers maximum configuration control over the operating systems. Stacked above the infrastructure is the layer designed specifically for developers, Platform as a Service, or PaaS. PaaS provides a hosted environment that comes preloaded with operating systems, databases, and development tools. By abstracting the underlying infrastructure away, PaaS allows software engineers to focus entirely on writing and deploying application code without ever having to configure or maintain the servers running it. At the peak sits the layer the general public interacts with. SaaS delivers fully built applications, like CRM systems or Google Docs, hosted by the vendor and accessed seamlessly through a web browser. Moving up these layers represents a direct trade-off. Organizations sacrifice the total configuration control found in IaaS for the turnkey convenience of SaaS. The buyer model dictates exactly where the cloud provider's responsibility ends and the client's begins, enabling organizations to precisely tailor their technology stack to their operational needs. The true test of this architecture occurs when an application experiences a sudden, massive spike in user traffic, the kind of event that routinely crashes physical servers. To meet this demand, a system can use vertical scaling, often referred to as scaling up. This involves escalating the power of an existing virtual server by adding more memory, storage, or CPU capability. However, vertical scaling is inherently limited. It eventually hits the physical performance ceiling of the underlying machine hosting the virtual instance, and upgrading it frequently requires system downtime. To solve this, modern cloud engineering relies on horizontal scalability, or scaling out. Instead of making one machine more powerful, horizontal scaling automatically adds new, identical servers to the network, distributing the workload evenly across a larger pool of computers. Because this method bypasses the hard limits of individual machines, it allows for theoretically infinite expansion with zero interruption to the user experience. Cloud elasticity works precisely because it treats servers as disposable, parallel units, rather than singular, irreplaceable monoliths. This parallel approach also solves the most inevitable truth of data centers. Eventually, underlying physical hardware will break. The architecture is built for cloud fault tolerance. If a component fails, the infrastructure continues to provide uninterrupted service to the underlying applications. This is achieved through hardware redundancy. Algorithms automatically detect when a server fails and instantly redirect operations to a parallel backup running an identical system. The same principle applies to software. Databases are continuously replicated across different geographic machines, ensuring no single point of failure can destroy the data. Depending on their specific security and performance requirements, organizations deploy this fault-tolerant architecture in different ways. This deployment model diagram illustrates the private cloud, which is utilized for maximum security and intra-business operations. Here, computing resources are governed and dedicated entirely to one specific organization, keeping sensitive data strictly isolated from outside traffic. This contrasts with the public cloud, where resources are shared among multiple consumers for standard business applications, and the hybrid cloud, which links private and public environments together to balance strict data security with immense computing power. The transition to cloud computing is a strict architectural reengineering. It extracts processing power from fragile, localized server rooms, transforming computation into a mathematically fault-tolerant, endlessly scalable utility.